shifts. So here it shifts to the right as you increase the model size. And secondly, when you fix the hyperparameter and you increase the model size, the performance actually is not monotonic. So you see, for example, if you fix the hyperparameter here and increase the model size, then you eventually get a worse performance. Okay, for example, right here. So this is a negative example of hyperparameter stability, and larger is better. Now, to see a positive example, we go to μp. So again, I didn't tell you what exactly μp is, but if you take that table I flashed earlier and just implement it and see what happens in practice, then what you see is that the optimal hyperparameters are stable as you increase the width of the model. And you always gain performance when you do so. Okay, so again, this is a very prototypical illustration of the stability of optimal hyperparameters and larger square. Now, in real life, when we're talking about things like transformer on X2 trained by Adam, the picture is essentially the same as the cartoon I showed you just now. So on the left, you have the standard practice of the standard way of scaling transformers, and on the x-axis, I plot the learning rate, y-axis, I plot training loss. Then you see that as the model gets larger, which is indicated by the darker and darker curves, the depth learning rate, which is where the depth occurs in each curve, it will shift to the left. And secondly, you can see that the curves are all crossing between each other, which implies that if you, for example, take the best learning rate for the smallest model, which will be right here, and then you try to use it on the largest model, which is reading off the value of this x-intercept on the darkest curve, then obviously the performance will be way, way worse than you will get on the smallest model itself. So this could be an explanation for this example I showed you earlier, where you try to try some technique on the smallest model and then naively try to scale up, and things that we do not desire. Now, on the other hand, on the right side, we use UP, then you see all the positive things that we care about. So the optimal hyperparameter is stable. On the right, you see, and the curves are not crossing, so you always gain performance when you go larger. All right. So again, these are all the things that we want from scaling. And furthermore, this is so here I'm showing you the most stereotypical hyperparameter, the learning rate, but it works for a lot more hyperparameters like learning rate, cross-degree temperature, initialization, standard deviation, linear schedule, so on and so forth. And in each of these, you can see the optimal is preserved. And in general, the true picture is that when you have, when you look at the high dimensional space of many hyperparameters together, then the optimal in that high dimensional space is approximately preserved as the width goes to infinity. So that's the key property of UP. So with this in mind, it's very natural to come up with what's called a zero-shot hyperparameter algorithm, which just means that instead of tuning the large model directly, which again can cost $10 to $100 million, you shrink the model to be very, very tiny, and then you tune that small model, and then just copy the hyperparameters back to the model. So this sounds super simple. Of course, like the key here really is that like the way you connect the large model and small models via UP. So when you have hyperparameters for the small model, you want to transfer it or copy it to the large network after scaling using UP. So that's the key to making this work. Of course, practitioners have for a very long time done something like this by using standardization, but this will essentially only work when the small model and large models are not that different. But with UP, you can essentially tune a very small model and have the hyperparameters work for arbitrary models. So as an example, we validate in our work, like everything I talked about so far, on models of a variety of scale, from like small models like all the way to GB3, 6.7 billion version, collaboration with OpenAI, and both vision and language models. So you can, so to summarize the results, whose details you can always refer back in the paper. There are two dominant trends when you look at the pattern here with models of varying scale. So the first is that when you try to apply muTransfer to these models, you can always compare it to the best hand-tuned baseline. So these are all previously existing models where like the researchers or engineers have tuned the model as best as possible on some benchmarks. So we can take those models and then retune them to hyperparameters using UP, right? So like you're just changing like running rate initialization for every layer of the network. You're not changing the architecture or anything, right? So this is like almost like, I mean, usually you will not be able to publish this. You just retune the hyperparameters, but this is the opposite case where like the whole point is to retune the hyperparameters, fix it. So when you compare the retune model, retune using muTransfer, compare it against the previous best hand-tuned, human-tuned baseline, then the pattern you see is that as the model gets bigger and bigger, the improvement due to muTransfer actually increases. So it doesn't decrease, but increases, which is usually kind of counterintuitive. Usually you expect it's harder to improve a better model, than to improve a worse model. I mean, there's a million ways to improve an okay model, but only a very small number of ways to improve very very good. But this is inverted, right? So here, the better the model is, the harder the model is, the improvement is actually bigger. So that's one very interesting aspect. The other pattern you can see from training and retuning this model is that the cost of tuning, the cost of applying muTransfer actually decreases with the model scale. When you compare it to fraction of the total training cost. Okay, here there's no mystery. The reason is that no matter what the large model is, roughly speaking, you can always shrink a large model to a fixed size model and tune that fixed size model. And the hyperparameters obtained from that fixed size model will apply to arbitrary large models. So here, therefore, tuning cost in this numerator essentially is constant, whereas the training cost here is increasing linearly with the model size. As a result, the relative cost of tuning will decrease inversely proportional to the model size. Right? So combining these two patterns here, it's almost like a free lunch. You're like getting better and better improvements for like less and less cost as the model size increases. Now for concreteness, we can look at this GPT-3 model. So this is in collaboration with OpenAI, and we took the 6.7 billion parameter model of GPT-3, and we shrank the model from 6.7 billion parameters to 40 million parameters, so around 150 times smaller. This is just purely shrinking the width of the model. And when we tune this model using muTransfer, we find that the resulting 6.7 billion parameter model is effectively the same quality as the 13 billion parameter model, so roughly double model size in some sense. When we look at the quality of the model, and the total cost of doing this whole procedure of retuning the model is only 7% of the final cost of training this model itself. Right? So 7% is already approaching negligible territory. This is not even the largest model in the GPT-3 family. Okay, so that's what I'll say about the reason we like to include the empirical impact of making on large models. So now the plan next is I'm going to tell you about what actually is NUP, which is a topic I picked. And then I'll talk about some of the theory behind this, like why do we suspect this in the first place? What are the mathematics? Let me pause here quickly for some questions, see if anybody has any.
So the GPT model, you said the 14 billion one performs as well as the billion one if you tune it with it.
So what that says is that if you retune your hyperparameters on a 40 million parameter model, the hyperparameters are trained can be used to train a 6.7 billion parameter model that is as good as a 13 billion parameter model. Like from the 13 billion parameter model from the
Are these experiments task independent?
A task dependent?
Yeah.
Yeah, they're all different tasks here. So GPT-3 is a language like internet, you're training on the internet. BERT is similar but smaller data set. This is machine translation, ImageNet, smaller machine translation, language modeling, image classification. So they're all pretty much
All are discriminative.
No. I mean, GPT-3 is language modeling. It's not discriminative. Yeah.
What kind of cost is associated with this applying NLP?
So the scaling itself, essentially, there's no cost. It's just a mathematical. It's just numerical, something numerical. There's no cost to it.
Yeah. So you said that for that skill set, which is increasing, you start from the initial the best parameterization to improve.
So you mean like
the way to get it right?
Yeah.
Is that you start from the best parameterization and then you use your algorithm to get better, right?
So okay. So to be precise, we take an existing model that already has some hyperparameters in there usually.
And you start from there.
Yeah. So we don't necessarily search in the neighborhood of that, but whether we like use it to like kind of like get a rough range of where things should be. Like it's a very coarse range, and then we search in that coarse range. So it's not you can think of it as like searching a very large thing. It's not like just searching a small.
There is no initialization and it's still working for small. Do you have something similar or perhaps?
Yes. Yeah, absolutely. Yeah, you can search in the entire space. The optimal. It doesn't depend on what
So so beginners in machine learning would say that want to train kind of large model, you would say for hyperparameterization directly use your method, right?
Yes.
Okay.
Yeah, there's no problem. Yeah.
So you said that you use 40 million parameters instead of 6.7 billion parameters for 15.
Yeah. So to get the hyperparameters.
How much cost does it take to come up with this number 14 million? That itself is an hyper.
Oh, that's it's very easy. So essentially, like from the smaller experiments, we found from our experience that it's always fairly reliable to shrink the model. So the width is 256. The number of neurons per layer is 256. So if you go below that, then there's a lot more noise in the hyperparameter tuning process. So the hyperparameters you get are noisy. So the quality decreases, for the same number of things you try. And then if you go larger, then the compute cost is large. So just from our experience, 256, the width being 256 for the small model is like roughly like a good point to tune on. And the 40 million parameter is essentially just shrinking the model to have width 256. Yeah.
Do you also make any approximation about the type of architecture in which this your approach will work? Is it agnostic about this architecture?
Entirely agnostic to the architecture. I mean, there's some subtlety here in the sense that like you really wanted to. Okay, so it's true like universal, but the way it's universal is that you need to know like kind of in some sense like in short you need to know test the program with like underlying framework to some extent to be able to understand how you analyze these architectures. But like there's like set of heuristics that I can describe in a second that gets you 90% of the way there for almost any architecture.
So also, what are the hyperparameters exactly?
Yeah, so you'll see in a second. Okay, so let's sorry, this is chat. Okay, please explain what is tuning cost. Tuning costs are very easy. Just I think like on a 40 million parameter model, for example, I don't remember the exact number, but maybe we tried like 100 different sets of hyperparameters. So we just randomly sample 100 different hyperparameters from the grid, and we try all of them. So we train the 40 million parameter to the end. Okay, and then we pick the best hyperparameter. Okay, so it's a very simple tuning algorithm because we don't want to do anything clever here. And the tuning cost is the cost of training 140 million parameter model times 100 because we tried 100 different parameters. And so like you can calculate the flops of that, and then the denominator training cost is the same thing, but 1 times the cost of training 166.7 billion. Okay. So let's move on. Let me explain what optimal differentiation is. Okay, so it always is very instructive to start with a simple example. So let's start with the simplest example, the multi-layered ceptron. So the equation of the MLP is given by this. So you have 3 sets of weights, W1, W2, W3. The input is denoted by psi. And there are some biases, okay, V1 and V2. So here, if you use things like PyTorch, in the default way you are scaling your hyperparameter is given by the standardization. So the way this works is something like the following. So you would initialize the weights W1 and W3 like the following, where W1 is entries, ID from a Gaussian with mean 0 and variance for Dn, where Dn is the data dimension. So Dn is the dimension of the psi. And then the middle and the upper layers have variance 1/n, where n is width of the model. So for example, W2 is n by n. And W3 here is like n by 1. So this is essentially like the variance is like 1/the input dimension of that layer. And then let's initialize the bias to be 0 and the learning rate let's denote by eta. Okay, so hopefully this is a very familiar description because again, you're using this by default if you're using something like PyTorch. Okay, so if you take this this formula and then you train neural networks using the scaling, then you get this set of plots. Right, so this set of plots, shows the optimal learning rate shifting to the left as you increase the model size. And also the best hyperparameter on the 256 width model will do very, very poorly on the largest model, right? Which is this one. So like this is a very ugly set of curves. Now let's try to see how μp tries to fix the situation. So μp is given by the following on this example. And the main difference between UP and SP, standard compilation, is given by these 3 purple bases. So the first place, we downscale the variance of W3 from 1/n to 1/n squared. Okay, so that means the standard deviation went from 1/square root of n to 1/n, or square root n to n. Okay, so this is the first modification. The second modification is learning rate of the last layer. So before we tie the learning rate across all of the weights, they're given by eta. Now we downscale the learning rate to eta and meters. Okay. So finally, we have a modification in the input layer weights, all the biases by upscaling the learning rate by a factor of n. Okay. So if I just drop this like this, you probably have no idea like why things are the way it is. And that's a very natural reaction. And you should have no reason to suspect this is the right way to do things at all. And this is a very natural reaction from every practitioner that would look at UP. So we'll explore why this is the right thing to do in a second. But if you just take this description and rerun your experiment, you'll see the right set of plots where things beautifully foliate the space, the curves are not crossing, the optimal hyperparameters are stable. You always stay in performance when you do grid analysis. So everything's beautiful. Okay, now let's look at the reason for these modifications. In particular, I'm going to focus on these two modifications. They will essentially give you the main points here, and then this is important, but kind of like secondary in terms of understanding. Okay, so to explain these two modifications, I'm going to first write out FSI, the upper network, trivially from a inner product to a sum. All right, so again, entirely trivial. I'm just saying FSI is the sum of n elements. Each element is a product of the output weight entry and the embedding entry, where like this phi da 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 is a abbreviation of this embedding. Okay, so firstly, I'm going to claim the following. So each entry of phi da 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 is going to be theta 1 throughout training. So by theta 1, I mean like each entry, if you look at the collection of entries of this embedding, then the typical size of these entries do not explode to infinity and do not shrink to 0. And that's what I mean by theta 1 as n becomes 1. Okay, so the claim is that like this will say theta 1.
Can you just be a bit more precise by the entry? Are you saying the input of our network, or you are looking at between two layers and what seems like it's always like that?
So I'm just looking at like this last part.
Okay.
This last part.
And what so the entries what is inside?
Yes. So
the
this.
function.
Yeah. So when you feed xi and you compute this part,
Okay.
right? You get a vector of length n.
Yeah.
Okay. So I'm just essentially looking at standard deviation.
Okay.
Over this length n vector. All right. So I just want to say like the fluctuation is constant. Right. Okay. Good. Okay. So again, the claim is that like this will be constant. The size of each entry will be constant as you scale the width of the network, and this will be true at any step of the time during training. Okay, so just to clarify, like the theta 1 here can be constants that depend on the training time, or other choices like data set, whatever. But I just want to say that like, the number inside here can be bounded regardless of n. Okay, below and above. Okay, so that's the claim, and this is actually very easy claim to verify. For example, if you set phi to be hyperbolic tangent, then phi is bounded, so like this cannot explode, and so you check that like it's lower bounded. So it's very easy claim to verify. So let's not do it on this. But once we see this phenomenon, it's very easy to see why these two modifications make sense. So the purpose of these two modifications is to ensure that each entry of W3, the alpha layer weights, has the total size of 1/n, inversely proportional to the width. Okay, let's first understand is this the case, and then let's understand the reason for keeping W3 1/n. Okay, so to see that this makes sense, we can check first initialization. When you randomly sample W3, well, the variance was modified to 1/n squared, so standard deviation is 1/n, which indeed implies that W3 initialization has total size of 1/n. Okay, so this is very straightforward. The less straightforward part is thinking about how W3 evolves over the course of training. Well, the way it evolves is through gradient descent is to add to W3, the learning rate times the gradient of W3. Well, the learning rate is on scale 1/n, so we just need to check that the gradient to W3 has order 1. Well, because of this claim that the entries of B is constant size, we just need to notice that the gradient W3 is essentially this B term times the loss gradient, the DLDF, and that's it. And DLDF is usually constant size because it's an error term. It is small, and you don't need to train at all. So that this verifies that the gradient of W3 is constant size, so multiplied by learning rate as 1/n, you get that the update to W3 has size 1/n. Okay, so hopefully this arithmetic makes sense. Again, so the consequence of these two modifications is that W3 now has entry size 1/n throughout training. And therefore, when you sum up n of these things, each of size 1/n times 1, which is 1/n, you can conclude that the sum cannot go up to infinity, right? But of course, it's possible for these things, the sum of n elements to cancel between each other because there's infinities. And this is indeed the case in initialization. The initialization, these terms are roughly independent across n. So this will indeed cancel, and this is really one over square root of n. But the final piece of insight here is that when you train the network, the different layers will get to know each other, and they will correlate, so that you actually cannot get too much cancellation in the sum. So that actually what dominates is there's a non-zero mean in the sum that will get picked out, which will dominate the second order fluctuation. So the conclusion is that this thing will actually be beta 1, will be constant size, and it will concentrate on a deterministic number that is the mean of each entry of this sum. Okay. All right, so we did all this calculation, and the conclusion is that the output network is constant size, doesn't explode to infinity, doesn't shoot to 0. It sounds almost like we did all this just for this. It sounds like is this worth it? Well, it's definitely worth it, especially when you train very large neural networks. So there's a very trivial practical consideration, which is that when you train these large neural networks these days, to do them efficiently, everyone uses very, very low precision format. So traditionally in scientific computing we use 60-bit floating point format, but actually this is way more than needed. And nowadays training of large neural networks occurs on for example 16-bit floating point FP16 or B16, which is 16-bit with 16-bit format. So the range of numbers that can be represented on these computers is much smaller than in traditional scientific computing. And if your network output range slows to infinity as you increase model size, then you're going to run into numerical issues much more frequently in large and small numbers. So if you imagine one of the beginning scenario, you're feeling very happy about your small goal, and then you try to scale up, and then the network just go out of range techniques everywhere. And of course, you're not going to get any value back. So this is just a very practical consideration, the numerical stability. There's also the algorithmic stability question of if you think purely mathematically, then this is the constant range of FSI, the upper network, is also important, because the loss function itself has an effective range, which is a constant range. For example, you square loss and your output is very large, then the gradient is huge as well, right? So there's feedback. And so mathematically, this is also very important to ensure that as you scale, the algorithm is stable. Okay, so hopefully that gave you some intuition for why we're making these modifications. And if you finally just compare this with the standard conversation again, where you don't have these modifications, and then you'll see that things will explode linearly with respect to width. And all these problems I talked about here will happen for the standardization. So okay, so this brings us to the table that I showed very early on, but I didn't explain, but we can explain it now. So this is the table where the x-axis shows the neutralization variance and the learning rate for HED, as well as the learning rate for Atom, another like popular deep learning optimizer you can find above this. And then the columns show different parts of the with input weights, biases, output weights, hidden weights. And then the entries tell you how to scale these hyperparameters and rows for the partial new network in columns. So in particular, like there's some colors in the entries here, and the way you read the color is that the purple plus black gives you UP, and then the gray plus black gives you S2. So for example, if you read these two entries, this says that the neutralization variance should be 1 with fan in squared, and the HED learning rate should be 1 with fan in for the output weights, where fan in again is like the dimension of the input of that layer. Then this is exactly what we talk about here, right? Yeah, and also this guy corresponds to this scaling learning rate. Okay, in any case, yeah, when we eventually talk about large neural networks, training of things like GPT-4, then you really need to talk about Atom, which is the default optimizer for these large language models. And you have to figure out what the scaling there is, and you can't do it. It turns out to be one of the fan ends for both output weights and hidden weights. And then there's some attention scaling. You know about that.
Previous slide. Yes, so I'm trying to reconcile this with like simple classification problems where you have like a softmax at the end.
Yeah.
So if such a network has to perform well, shouldn't it be such that certain weights are very high and the others are very low? And so
Sure.
You know, the softmax becomes very close to 1.
Sure.
So how does that square with the same all the weights are at the same scale?
So softmax largest to softmax would be FSI, right? And here I'm just saying that like the numbers should not scale, the size of numbers should not scale with width. But you can train for a very long time. And the logics can have scale, like between, like there are 10 logics, you can have one that's very big, the other are very small. And that's fine. I'm just saying that when you vary width, like this phenomenon of like, like one logic is very big, the other is small, like this should be like consistent as you know, right? So all like as a function. Okay. Okay, so the point here is that like kind of with the earlier question of like which architectures covered, essentially this table will cover like 90%, 95% of architectures out there. Essentially any natural architecture, like you essentially can derive the right thing most stable. For the rest of them, you can still derive it, but just think a bit harder about like how the picture actually maps to the underlying structure called the program. But if you do so, it's also very easy. Okay, so now the plan next is I'm going to tell you about some math behind this. So let me pause here briefly and I guess question.
But perhaps you speak about it. Because you need to say with respect to the Brazilian right? It means that you have some assumption and right.
Very much. Very much.
The facts. So you don't have any problem if you don't have to transfer between and things like that, because actually this is what's happening is kind of free practical networks. You have no transfer here everywhere. When PyTorch shows that it don't really understand what's happening there.
Yeah, so okay, so if you look at the proof, essentially what I'm assuming here is, okay, first of all, the rule, can be just derived without kind of
You can always
Yeah, okay. So the key, important theorem here is to show, I'll tell you about it later, but you need to show the existence of certain infinite web numerals. Okay, so you need to show certain limits exist mathematically, and there you need some assumption on the nonlinearities to make the proof go through. But it's not it's just to make it easy. Yeah, and there the assumption is actually quite mild. The nonlinearity needs to be roughly speaking, the nonlinearity of the neural network needs to be has to have a second derivative, which is polynomial now.
And because
a weak derivative is
oh, yes. And what kind of theory are you talking about? Because, is it diffusion, okay.
So can this question be framed in even a very simple case of linear regression with an infinite large bit scaling with it? If I investigate the solution as a function of it, do these conclusions hold?
For linear regression?
Yeah.
It holds trivially because there's no width in linear regression, right? The input and output dimension are fixed, and there's no hidden dimension.
But if you take, for example, this kind of stochastic neural network where you put the weight randomly and only the last layer is optimizing this case, you can increase it. And that's kind of result that it's
So that's the classical random feature
exactly
model. And I would say that if you look at random feature models through this framework, it will just tell you the opposite thing. The obvious thing. The obvious thing is that you should train the whole network minus the last thing. Essentially. That's the obvious conclusion. It's not very interesting. If you're studying random features. Okay, so let me try to move on and give you some perspective on the math. Okay, so first of all, let's talk about what is the parameterization. So I already used this word many times, and UP is an example of parameterization. And this is, of course, the table we just saw of UP. Now, the notion of parameterization is essentially just any particular way of filling this table is a parameterization. So here I said 1 over fan n, but this could be 1 over fan n square or fan n square root. So any particular way of filling this table using for example powers of fan in or fan out is a parameterization. So such a way of filling the table essentially is a rule that tells you how to scale the hyperparameter changes. So you might say half the learning rate when the width doubles, but it's not going to tell you, how to set specific values on specific model sizes. So you will not ever say use learning rate 1 negative 3 with 10 points. Okay, so this is not something that you can say. This is too precise. The table is a Corsair rule that just tells you how to change the model size. Okay, so, and this is for good reason because this rule probably is going to be wrong on some data set, but the scaling rule is likely to be robust everywhere. So one way to think about parameterization geometrically is that it's kind of a flow of hyperparameters with width. So pictorially, for example, if you plot the hyperparameters on the x-axis and then plot width on the y-axis, you can think of width almost like time. And you can think about how if we start with the hyperparameters for width 100, how should they change as the width becomes smaller? So it's a flow of hyperparameters. And different parameterizations are just different flows. So, for example, SP on the right, in the default way of expressing hyperparameters, the learning rate is fixed as you increase the model size. But in UP, the learning rate is scaled, to decrease with width or in various ways with the company. So in this kind of geometric and graphical intuition, parameterization is like a slope of this flow, and it's not intercept, right? It's not like a particular value width to 24. And defines the direction toward infinity. Okay, so of course there are many ways to go toward infinite width, many different slopes. You know, for example, you can look at ST and you can like try to like push the hyperparameters through this flow toward infinite width, kind of like running it for infinite time somehow. And when you do so, like the neural network, the really wide neural network will exhibit a certain set of behaviors. We call it the standard hyperparameter or ST limit. And likewise, you know, for the same hyperparameters and with 100, you can push it in another direction, which is another parameterization like UP, and you get some other kind of limit called the feature learning limit that the network exhibit this kind of behavior with is very large. And then finally, you know, another kind of parameterization like neural tangent parameterization, which I didn't talk about so far, but some other kind of parameterization, and if you push the hyperparameters toward infinity, the neural network will exhibit some other stuff. So obviously, you know, like this is 3 examples, and there's like an infinite number of possibilities for how we scale. And so there's an infinite set of potential possible behavior of the neural network when you push these hyperparameters to infinity via any particular parameterization. And here's an obvious, you know, observation, which is that, you know, the parameterization, in the way I defined it, is bijective with quote unquote infinite width neural networks. I mean, the bijection is, you know, I take the limit of a finite width neural network in the direction given by the parameterization, right? That goes from left to right, and from right to left, it's just that the infinite width neural network has to be defined by a way you take the limit. Like the infinite width has to be defined by the way you take the limit, and the way you take the limit is precisely. Okay, so it's kind of like on the left is like slope, and on the right you just find the slope. Okay, so this is all, you know, like fairly trivial things. Nothing is really happening here. I'm just kind of describing a mental picture of how you should think about this. Now, let's come back to why UP should be able to preserve the optimal hyperparameter. And so here, you know, the question is like, if you know how you can, you know, if you know how the optimal hyperparameters will flow as you take away the, right? So like, sorry. So again, if you know how the optimal hyperparameters for each width look like. So it's like some curve that goes to infinity, and you know, and as mortals, we can only ever see a very small part of this curve. But of course, like when you want to train these large models, you want to like predict what the curve will look like without actually looking at the specific points on it. So essentially, the question is like asymptotically, if you look at the curve of the optimal hyperparameters, which parameterization does it look like asymptotically? Right? But which is the best? Best in the sense like, you know, like which one predicts is more aligned with how the optimal hyperparameters look like when the width is large. Okay, so this brings us to what I call the scaling thesis, which is just that, you know, the optimal parameterization corresponds to exactly the optimal limit. Now compare this with previously where I said parameterization, you know, corresponds to infinite width neural networks, which is obvious. This is less obvious that optimal parameterizations correspond to the optimal limit. And the way I phrase it, of course, makes it sound obvious, but to arrive at this conclusion, it takes a little bit of thinking. So what I mean, first of all, by optimal parameterization, well, you should have 2 properties: the stability of optimal hyperparameters and the larger is better property, which are exactly what you saw, you know, in the beginning of the talk, if you remember these curves. Okay. And again, these are like very desirable properties of scaling. And if larger is not better when you scale, then you should not scale. Okay, on the right side, what I define as optimal limit is just a mysterious statement that, you know, you should have maximal update, maximize feature learning. I have not talked anything about this at all so far. So, you know, it's okay to be confused at this point. I'll explain in a second. But let me just observe that, you know, the left side is something like super like empirically important. When you try to scale, you should be stable in hyperparameters. You try to larger is better, and it's like very empirically important to actually achieve these properties. On the right side, you have something entirely theoretical, something entirely in our imaginations, doesn't exist in reality. But if you believe in this thesis, there's a direct bridge between them, and you can shift any mathematical bands on the right side to GPT-4, GPT-5, GPT-7, like any of your favorite art model or vision model or anything. So this is a very precious idea in some sense, because there's this direct bridge between theoretical bands and empirical bands, which is rather rare. And also remark just that like the way I phrase it, this is a thesis that's independent of the motion model size. So obviously we're focused on width here, but you can also talk about this with depth and other experts. Okay, so I'm going to dive into this topic in a second and talk about the mathematics behind this. But let me, for the second, just illustrate as vividly as I can that μp indeed is the unique optimal factorization. I mean, this is implied by this because μp will be optimal limit. But let me just show you that the left hand really is true. So in this animation, on the right side, I'm traversing a 2D space of parameterizations. So this 2D subspace of parameterizations contain UP and ST, towards default. And then the green dot, is traversing some trajectory that contains these 2 points. So in other words, like every position that the green dot lands on is a particular way of scaling the networks, scaling the linear rate translations. Okay. And on the left side, I'm just plotting the curves you've seen many times already, where the different curves correspond to larger and larger models. Where at any given instant, the way the model is scaled up, the way the learning rate initialization is scaled up is according to parameterization occupied by the green dot on the right. Okay, so you should obviously take away 2 things. One is that only when the green dot is on UP, you have the stability of hyperparameters like right now, and the non-crossing of curves, the larger scatter property. And secondly, when the green dot is off of UP, none of these the hyperparameters are shifting and the curves are crossing. Things get ugly. Okay, so hopefully this conveys this important insight. Now let's go to the right and let's talk about what is meant by optimal limit. So the way you can understand this thesis is essentially by a 2-part argument. The first part is the pure mathematical argument. This will classify all possible infinite width limits. So this will so I'll show you pictures essentially second, and this will contain things that a lot of people know, like internal and process and the feature models, but also new things that people didn't discover. And then we essentially go through a process of elimination to see which one can ever correspond to parameterizations that have these 2 properties of hyperparameter stability and larger spectrum. And so this is kind of like quote-unquote physical argument, not because we need to use physics, but because we need to use our intuition of what works and what doesn't work in practice. Back to this later. Okay, so the mathematical part is called the dynamical dichotomy theorem, and this is essentially a classification of all possible parameterizations and their infinite width limits. This is a very high dimensional space. For example, if you have L layers, the space is at least formed by initialization and learning rate for each layer, so that's 2 times 12 dimensions. But of course, we cannot represent this on paper, so I'm projecting it to 2-dimension through some kind of artistic projection to get the main idea. But the point here is that most of the space of factorization is junk. So training blows up or training gets stuck in initialization when the width goes to infinity. They're not interesting. But if you squint very closely, there's an island in the middle of junk that actually contains more interesting things. And most of the points on this island was called the kernel regime. So this means that if you pick a point here and you take width infinity, a point the rule there, then the neural network at infinite width will evolve under gradient descent as a kernel equation, like so. So this says the change in the function represented by the network due to one-step training is equal to essentially a kernel k times the loss derivative at the current function. Okay, so in particular, k here is fixed throughout training. Essentially, it's determined by the neural network architecture and computation. And this is, as a mathematician, this is a beautiful thing. You have simplified a vastly complicated neural network to a simple one-line equation that everybody understands. That's linear. For example, if you pick the loss function to be squared, this is exactly a linear equation, super simple, like beginning, undergrad level math. But the tragic thing here is that this model, alluringly simple, doesn't capture what actually matters in practice, which is feature learning. It's like the learning of representation of the inputs, like having an internal representation, a learned representation of a picture of a cat, a picture of function, like that kind of thing. So any point in this kernel regime that satisfies this kind of equation will not have feature learning. So these do not describe the neural networks that we love in practice.
The question, in all this, are you assuming the depth is fixed?
Yes, fixed depth. Width goes infinity.
So is that also reasonable because the depth can never scale at once?
Yeah. So for various reasons, it's reasonable. For example, like in practice, the depth doesn't increase that much, but the width can increase more. Like the width is much larger. I mean, the depth is like usually at most 100. The width can go up to like 10,000.
But when people use this kind of net architecture and trying to be some kind of differential equation behavior, this case in some sense like having the depth of infinity.
Yeah, in a specific way. I mean, so you can talk about ResNet as used in practice, like practitioners like images. You can also talk about neural ODEs.
Yeah,
that's a different kind of ResNet. And for example, the weights are high here. So it's like dynamics are different. So in the former case, in the real ResNets, like I said, like the depth is no more than 100. Right? In the latter, of course, it's dynamic. You can make it, you want to make it more accurate, increase depth. So that's a different problem. Okay. Great. So again, most of the space is junk. There's an island in the middle that's not junk, but most of the points fall into the kernel regime that satisfies like alluringly simple equation, but does not actually have the feature that we care about with this feature line. And this includes the tangent kernel limit and then the standard contribution with one over width learning rate. But finally, the last piece that is missing here is this upper border here in solid hope, which contains all the parameterizations whose limit actually plus feature. So let me just reiterate: the feature learning here means, at the very least, that when you look at, for example, the grand matrix of the last layer embedding of all the inputs, right? So this is kind of like roughly kind of like a notion of matrix of distances between the embeddings. Then like this grand matrix should evolve over the course of training. Okay, so that's at least like the basic, very basic minimum of doing any kind of feature learning. And so in the kernel regime, this is the parameter does not evolve. It's fixed initialization. And roughly speaking, it's like essentially the same as the kernel here. But in feature learning, this parameter evolves. Okay, so that's like the basic minimum of doing feature learning. Okay, so this is describing the feature learning is describing this upper border here. And then finally, if you spin it closely, you see this point called maximal update, which is of course UP. And this essentially does the maximum amount of feature learning in the sense that like in any layer, you will see features involved, right? So if you like, so as a negative example, if you pick a point off of this point right here, maybe like the first layer is not learning, it's like fixed initialization, and the second layer, third layer are learning features. So that would not be max. So you know, on the contrary, maximal update is learning every single parameters to have a feature. Okay, so this is essentially the main theoretical result. Of course, you know, the actual math is much more complicated, but this is a very high-level summary. And then finally, we have a very short physical argument that just goes through the list and see like which one can possibly correspond to prioritization that has these two properties: higher parameter stability and larger scatter. And this is, you know, very, very simple once we do all the hard work to classify the prioritization. So obviously the unsavory attributes cannot do this, right? So then I just look at the kernel regime prioritizations, and there are many reasons that should not be optimal. For example, we just learn features, and you can also just look at concrete performances on real data sets of the kernel limits versus finite networks, and you see that the kernel limits actually do worse, so you cannot satisfy larger better. And then finally, you look at the feature running prioritizations, and you know, like I said, like mup is obviously the optimal one if you're in feature running regime. So essentially that's it. Like, once you have again the mathematical picture, it's very easy to see which limit should be the optimal limit that corresponds to this optimal calculation. And then you can just experimentally verify that everything works. Okay, so now let me just try to quickly conclude. Let me just kind of zoom out a little bit and look at, you know, some of the triumphs of theoretical thinking, which is to a very large degree like the biggest triumph of mathematics is in physics. So for example, in physics we have understanding that like our universe is formed by 4 fundamental forces: gravity, electromagnetism, nuclear and strong nuclear force. And then we have 2 amazing theories called the Standard Model and the General Relativity that describe these different forces. But the theory, everything that unites these 2 models into a single model that describes all 4 forces has been elusive so far for the last century. And in deep learning, we have a very similar situation where we have fundamental forces like width, depth, training time, and so on and so forth, which are ways you can scale your deep learning system. And in some ways, you know, like this thing called tensor runs, which is a theoretical framework that underlies everything I talked about, gives a very satisfying theory for what happens when we take width to infinity, but you know, fix everything else. Right? So that's kind of like looking at gravity isolation to everything else. But you know, the world is much larger than just the width. You know, we have depth and training time, so on and so forth. These are all fundamental scaling dimensions of deep learning systems. And compared to, you know, our understanding of physics, these different other fundamental forces of deep learning are much less well understood. And just like, you know, in the 19th century, Maxwell was able to unify electricity and magnetism, likely we'll be able to unify many of these apparently separate fundamental forces in plane. So as such, right now is really good time to look and to build this theory of everything for large scale deep learning, which would answer the question of, how do you scale hyperparameters optimally for depth, training time, so on and so forth, but also how should you allocate your resources across these dimensions when you try to scale your model. And if you believe in the optimal scaling thesis, like I talked about, then for a mathematician, it's very easy to contribute. Well, the roadmap is, you just focus on the right side, you try to take infinite size limits, you classify all possible limits, and you find an optimal limit, just like I presented just now. And it's very easy to have a huge amount of impact from this theoretical work based on this bridge between empirical and theoretical advances. And if you look at these highlighted points, taking limits and classifying objects, these are things mathematics is really, really good at. And lots of fields medal, including some from last year, that's been done, that's been awarded for taking limits, classifying objects. Okay, so I'll end here. This is the paper that I talked about today. And again, you can already use muT, but if you install muT, you use PyTorch, we can look at the source code by going to github.com, Microsoft muT. All right, thanks, guys.
Thank you for the report. Any questions?
Yeah. So I think the perhaps tonight, can you go back to the previous slide? Perhaps it's a really naive remark, and I'm sorry for that, but we talk about the training time. But I have two problems with the way you say it converts to training time. First of all, if we just look at the gradient perspective and we look at the differential equation as we take with gradient, training time is just a matter of scale, right? It's on some, you can just do a change of variable and just take your training time and the alpha, which is actually in all your gradients, right? And you just optimize between 0 and in some sense, right?
Yeah.
So I'm first saying that we did not direct to apply exactly everything that you said in training time. And also, you say take everything to infinity. But then taking training time to infinity is really, really special, right? Because it means that we want to converge to the optimum, and it means that there is a lot of problem to wanting to converge to the optimum, right?
Yes.
First of all, is do you really want to converge, not the output, right? You need the test set, right, to compare with that.
Yes.
Because and things like that.
Yeah.
When it's kind of
Yeah, so all of what you said is kind of important questions to ask in this thing. So but more concrete, okay, so first of all, yeah, so you can kind of obviously take the continuum time limit to get a differential gradient. So first of all, that's kind of somewhat debatable. Whether that's actually a good limit or not, because I mean, people want to take big steps, not small steps. So first of all, it's very debatable whether that's a good model to study. And secondly, just as you said, different choices, hyperparameters or algorithms will make you arrive at different points, of the parameter space. And so the one mission here is to understand where the eventual minimum local or global minimum that you actually arrive at. And what does it actually look like, for example? But definitely it's very true that training time is somewhat special.
Exactly. I was feeling that in terms of scaling, I'm not sure. I don't see it working that way, but it's really a naive intuition, right?
Yeah. So I mean, the reason it actually does make sense, for example, is you can get a sense from the empirical work people have already done. People have already studied what's the right amount of training time you train for certain model size. Right? So this is an empirical thing you can kind of extrapolate what is the right
about if I increase the width, then I should increase, I double
Exactly.
the train. Oh,
Exactly, right? So how do you allocate your resources across training time with so that's a very important question that has already been explored in pure. But of course, a lot more theoretical questions.
so this is where you go to infinity, right? Because for us, we take the width to infinity, so you know that you have to train in some sense to infinity, right? Just to understand what's that.
Yeah, it's more subtle than that, but yeah,
That's
baby step. Okay, any other questions? There were some questions on the chat. Okay, never mind. Okay, any other questions?
So this, you said in one of the limits, it looks like a function that evolves as a gradient set. What's the notion of time there? Like how many time steps do I think of that?
Like, are you talking about like right here, like this guy?
Yeah.
Yeah.
So
So
you first set the size of the system and then you're doing time step.
so the way you should think about it is very simple. So like have you like written code, a deep learning code? Okay, so then you know how this. So like you think about the following. So you essentially fix the training time. You fix your program. Okay, so you're taking large steps, whatever. You fix the program, and then you just take the matrix size to infinity. So that includes initializing randomly initializing the model, and then calculate the gradient. You train it for 100 steps. Okay, then you take the infinite limit. That's it.
So the notion of time is
It's the same, exactly the same as what you write. Right? There's no continuum time limit here. It's literally discrete. Exactly what you write. Yeah.
So maybe I'm missing something, but we showed one table where you basically gave a rule of thumb that how should you scale different hyperparameters. And earlier you also showed one picture, one diagram where you showed that okay, you fine tune your model on a relatively smaller. You fine tune a relatively small model and then kind of use those hyperparameters on the big larger model. So I didn't understand how. How is fine tuning happening? I mean, eventually you are just giving a rule of thumb, right? That okay, one by scale your hyperparameters by one by fanning and stuff.
Yeah. So let's look at the table.
So I mean, if that is the rule, then why should I continue? I can directly use it. So I think I'm missing something.
Yeah. So let's think through this. So let's first think about like the naive will do. Okay. So you can first of all, we're not fine tuning anything. We're just tuning the hyperparameters. So we're just like say on optimize the hyperparameter. The most naive thing to do is like I randomly pick 100 set of hyperparameters and then try them all and pick the best. So that's hyperparameter tuning. It's not fine tuning. Fine tuning is like you take the training model. I think training on that. Okay, so all right. So the naive thing, if you don't know the naive thing to do, if you want to use a small model, is you tune a small model. Say you try 100 different hyperparameters, you get the best one, okay, and then just copy it to the large model. That's a naive thing. That's like standard calculation. Okay. So this will not work because essentially, like the larger the model is, the naive way of scaling will just scale the model like away from the so if you remember this kind of picture here, like if the optimal hyperparameter is more like UP, so if you're still using SP, like the distance between the optimal and how you scale is gonna be farther and farther apart. Okay, so this is not optimal. So the point of using the prioritization is that the guarantee is kind of the following. So the guarantee is that if on a small model you give me a set of near optimal hyperparameters, then this scaling will roughly preserve this analysis of scaling. Okay, so if you don't tune the hyperparameters, then there's like no guarantee is there. Okay, so I mean you will like in general, if you have a good hyperparameter for a small model, you also have a good hyperparameter for a larger model. But there's not really any guarantee that it's going to work.
Okay, there are no more questions and close the session. Thank you, Dr. Young. And there are any questions outside, please.